This is the most dangerous thing inside a nuclear submarine. The air the crew has already exhaled. In our last video, we talked about how a modern nuclear submarine can stay submerged for months on end. Its real limit is not fuel or oxygen, it is food. But that framing skips over a much darker truth. If the life support systems aboard a submerged nuclear submarine powered down for just a few hours, the crew would not starve to death. They would not even suffocate from a lack of oxygen. They would be poisoned, slowly and silently, by their own breath. A modern nuclear submarine is a sealed steel tube carrying roughly 130 people through the deep ocean. The moment its atmosphere stops being actively rebuilt, that atmosphere begins trying to kill them. The reason these boats can stay down practically forever comes down to 3 machines, each fighting a different chemical threat. This is how a nuclear submarine makes its own air. Start the clock the moment the hatches seal. From that instant, every person aboard is consuming oxygen just to keep their cells alive. Multiply that across a crew of 130, and the submarine is burning through more than 3,000 liters of breathable oxygen every hour. But oxygen depletion is the slow death. The fast death is what the crew is putting back into the air. Every breath a human exhales contains roughly 4% carbon dioxide, a waste gas the body produces by the kilogram every day. Outside, in the open atmosphere, that carbon dioxide dissipates into the air. Inside a sealed submarine, it has nowhere to go. And carbon dioxide is not a passive bystander. At a concentration of just 1%, the crew would start getting headaches and feel drowsy. At 3%, breathing becomes labored and judgment begins to crumble. At 5%, with plenty of oxygen still in the air, the human brain starts to shut down. Cognition collapses. Consciousness follows. The crew suffocates not because they ran out of air, but because the air filled up with the wrong gas. And carbon dioxide is not even the most dangerous thing in the air. A nuclear submarine does not just need to make oxygen. It needs to defeat the atmosphere 3 different times, in 3 different ways. The Central Atmosphere Monitoring System, called CAMS, coordinates all 3 machines continuously, tracking every gas concentration in real time to keep the crew alive. Start with the simplest problem: oxygen. The system that solves it is the Low Pressure Electrolyzer, called LPE, and it is located deep in the engineering spaces of every modern Virginia-class and Ohio-class submarine. Its job is to split water molecules and return the oxygen to the crew. The chemistry is familiar from high school. Pass an electric current through water and the molecule splits. Hydrogen collects at one electrode, oxygen at the other. 2 parts of water become 2 parts hydrogen and 1 part oxygen. On paper, this is the most basic reaction in chemistry. On a submarine, it is the only reason these boats can exist as we know them. The trick is the water. You cannot electrolyze seawater directly, because chloride ions react at the electrode and produce chlorine gas, and chlorine is exactly what the crew must avoid breathing. So before any electrolysis happens, seawater has to be desalinated, either boiled and condensed back into pure distillate, or forced through reverse osmosis membranes until the salts are gone. Only then can it be fed into the cells. Inside the LPE, that purified water flows through a stack of solid polymer electrolyte membranes, thin plastic sheets that act as both the electrolyte and the insulator. A heavy direct current passes across each cell and the water comes apart. The hydrogen, which would be catastrophic if it accumulated indoors, is collected and vented overboard into the sea. The oxygen is released into the ship's atmosphere at near ambient pressure. This was not always so elegant. The first electrolyzer ever sent to sea, Treadwell's Model 7 L16, was installed aboard USS Nautilus in the 1950s, running at 3,000 pounds per square inch. The modern low-pressure electrolyzer does the same job at ambient pressure, in roughly a third the volume, and it runs unattended. But none of this would matter without one thing the old diesel boats never had. Electrolysis is hungry. A few kilowatts buys you only a trickle of oxygen. To keep more than 100 people breathing for months without ever surfacing, you need a power source that can pour energy into the cells continuously and never run dry. That is what the S9G reactor core is for, the nuclear reactor that powers Virginia-class submarines with enough electricity to split water around the clock. Now the real fight begins. Of the 3 machines aboard a submarine, the one that does the hardest and most thankless work is the carbon dioxide scrubber. Inside that scrubber is a chemical that has been quietly saving submariners' lives since the late 1950s. The chemical is called monoethanolamine, known as MEA. It is a colorless, slightly viscous liquid, faintly fishy in smell, and it belongs to the amine family, organic molecules built around a nitrogen atom that loves to grab onto anything acidic. Carbon dioxide, dissolved in water, is mildly acidic. Cold monoethanolamine reaches out, locks onto a carbon dioxide molecule, and holds it tight. Heat the same solution to boiling, and the bond breaks. The carbon dioxide comes back out. The monoethanolamine goes back to hunting. That single reversible reaction is the entire basis of submarine air purification. Think of it as an artificial lung. Inside the scrubber compartment, a solution of monoethanolamine, MEA, in water cycles continuously between 2 towers, inhaling and exhaling on behalf of the entire crew. The first tower breathes in. The ship's atmosphere is drawn through fans, pushed up through cascading MEA, and as the air passes through, the carbon dioxide dissolves out of the gas stream and stays behind in the liquid. The cleaned air leaves the top of the tower and goes back to the crew. The second tower breathes out. The carbon dioxide-saturated MEA is heated near the boiling point of water. The chemical bond reverses. Carbon dioxide fizzes out of the liquid, is collected, and is pumped overboard, dissolved into the seawater the submarine is gliding through. The regenerated MEA flows back to start again. This lung never stops. It cycles 24 hours a day for months without pause. A modern scrubber holds atmospheric carbon dioxide below 0.5%, an order of magnitude under the level where cognition would begin to fail. Monoethanolamine, called MEA, is not without costs. It degrades under heat and oxygen, slowly producing ammonia and formic acid and other compounds the crew can smell. The vapor permeates the boat, and every uniform, every page of every paperback, every blanket takes on a faint chemical tang that submariners carry with them long after the patrol ends. The Royal Navy examined that smell and the corrosion problems and switched some of their boats to a molecular sieve system in the 1970s, using engineered zeolites with cavities sized precisely to trap carbon dioxide molecules. Different chemistry, same idea. In emergencies, submarines also carry lithium hydroxide canisters as backup, solid chemical absorbers that can buy time if the main MEA system fails. Either way, the result is the same. The submarine breathes out, and the air stays safe. The third machine handles what the first 2 leave behind. When the scrubber pulls carbon dioxide out of the air, that air still is not clean. It carries hydrogen leaking slowly from the battery banks. It carries carbon monoxide drifting off electrical insulation and galley equipment. It carries methane from the crew. And it carries a stew of volatile organic compounds evaporating from paint, lubricants, fuels, and adhesives. Every porous material on the boat slowly outgassing into the same closed atmosphere. None of these would do much in a normal building. In a sealed submarine, they accumulate day by day. Hydrogen is the most urgent. At a concentration of just 4% in air, hydrogen becomes explosive. A single spark from the wrong switch, and on a submarine there are thousands of switches, could turn the boat into a bomb. The third machine, the catalytic burner, exists primarily to eliminate that risk. The principle is straightforward. Submarine air is drawn through a chamber, heated, and passed across a bed of catalyst. The catalyst, traditionally a manganese copper oxide compound called hopcalite, lowers the activation energy required to oxidize the contaminants. Hydrogen burns into water vapor. Carbon monoxide burns into carbon dioxide. Trace hydrocarbons break down into the same two products. The boat doesn't have flames. It has, in effect, a slow, continuous combustion running inside a steel can in the engine room. The carbon dioxide produced by the burner is handed off downstream to the monoethanolamine scrubber, which removes it the same way. Removes the crew's exhalations. The water vapor goes into the ship's humidity control. The atmosphere comes out cleaner than it went in. The burner has one very dark chapter in its history. In the early days of fleet ballistic missile patrols, a catalytic burner did exactly what it was designed to do, but with the wrong feedstock. Refrigerant gas, a chlorofluorocarbon from the air conditioning system, leaked into the atmosphere and reached the hot catalyst. Instead of being torched into harmless products, the chlorine and fluorine in the refrigerant recombined into phosgene and hydrofluoric acid, two of the most toxic gases known to man, manufactured in real time inside the ship designed to keep them out. Modern systems use catalysts tuned to minimize refrigerant decomposition, with lithium hydroxide adsorbers downstream to catch any acid gases that do form. The lesson was hard, but it was learned. By the time the air leaves the burner, the third threat is gone. 3 machines. 3 different chemical wars, all fought continuously, and all inside the same sealed steel hull moving silently through the ocean. The electrolyzer cracking water for the oxygen the crew is burning. The amine scrubber pulling back the carbon dioxide before it reaches the brain. The catalytic burner torching the trace gases before they accumulate into something explosive or toxic. None of them would work alone. Together, they replace what an open atmosphere does for every other human being on Earth. For free. A nuclear submarine is not stockpiling air for a long voyage. It is not rationing oxygen out of bottles in the ballast tanks the way the first nuclear boats had to in the 1950s. It is manufacturing the atmosphere continuously from seawater and electricity and dumping the waste back into the ocean as fast as the crew creates it. The S9G reactor provides the power. The machines do the work. CAMS monitors everything. The crew lives inside the result. The limit is food. 3 steel machines have made the toxic bubble inhabitable. Everything else is just groceries.